Section 6. Implementing Advanced NLP Methods. In this section, I'm going to briefly introduce a couple of advanced NLP methods. They're not the core main techniques you would likely be using every day, but they are very powerful, so it's good to be aware of them. The first is the word-to-vec vector space model implemented in GenSim, and the second is part-of-speech tagging using Spacy, working with vector space models. In this video, we're going to take a look at the word-to-vec algorithm to construct a vector space language model, and then we're going to look at some uses of a trained vector space language model. So each dimension in our vector space represents a word. So the number of dimensions is equal to the number of words in our vocabulary. So we tend to be dealing with very high dimensional spaces. In order to determine where I should place a word in this vector space, what is the correct positioning of that word, I want to consider the association between the word I'm placing and the word representing each axis. So for example, if I'm looking to place the word dog into this vector space, it would have a relatively big projection, a relatively big overlap on the axis representing the word cat, because cats and dogs tend to be associated together in language. So what we find is words that have very similar contexts are found very close together in this vector space. As a result, we can find vectors of meaning within this data. Now this is a very profound method, but actually it's relatively simple to train. The basic idea is to take a large amount of text, to define a focal word within this text, look at the context around this word, and by churning through a very large text corpus, learn the frequency with which different words are associated. If we consider this sentence, I have a focal point in blue and context words in red. In this case, my context is 5 words before and after the focal word, but it could be defined slightly differently. What I would do is record England as the focal word in this first line, and I would count that it's been associated once with all of the words in red. Then I would proceed to the next focal word, in this case and do the same thing. And I would slide that window across a large amount of text and record the frequency with which different words are associated in order to build up a probability distribution of association. In a very simple case, this would look something like this. You could imagine that I have a very small vocabulary of only 3 words, so each word would be a point in this 3D space. And the overlap, the actual components of this vector, would indicate the probability of association between the word represented by the blue point. So the component of each vector representing where the blue point is placed tells us the degree or the frequency of association between the word represented by the blue point and the word represented by each of our 3 components. So in this case, the strongest overlap is in the first dimension with word 1, which has a component of 0.5. You can jump into a notebook just to get a slightly better idea here. So let's go ahead and install a few bits and pieces that we're going to need. We're going to make use of the brown corpus, which is available in NLTK. I've already grabbed it, but go ahead if you need to. And the brown corpus is a reasonably sized corpus. There's about 57,000 words. Go ahead and grab those sentences. And the sentences are pre-tokenized for us. First thing we're going to do is train a model based on this text. So GenSim will work through each of this text, look at the context and the focal words, and build up this model of association and this vector for each of the words. This is a relatively small corpus, so it doesn't take too long to train. We have a few options in here. Most of them concern the dimensionality of the vector space, in other words, the size of the vocabulary, and exactly how we define our context. So our context could be just words before or just words after or both, and it could be of a variable size. Once we have a trained model, we can interrogate it and ask it some interesting questions. Let's ask the model what are some similar words to the word mother. The model is able to look within the vicinity of mother in this vector space and tell us some similar words. And it gives us back the 10 most similar words: father, husband, son, brother, wife. Likewise, we can ask the model, is there an odd word out? Within king, queen, prince, and Edward, it rightly finds that Edward is the word that is the odd one out. And that's because Edward does not belong in the vicinity of the vector space that king, queen, and prince belong to. As I mentioned, if we're dealing with a very large vocabulary, in order to train a model on that very big space, we need a correspondingly large amount of data. Thankfully, Google has created word vectors for us by passing through a huge corpus of news. And we can go ahead and grab those. There's a link in this notebook. And that saves us really a lot of training time. What we're going to do is a quick visualization of this space using a principal component analysis. The idea of principal component analysis, or PCA, is to find a low-dimensional space from this high-dimensional space. And this allows us to visualize what's going on in this very big vector space model. And then we're going to take a few words and plot them in this space. And hopefully we should see that similar words appear together. So we have Paris, London, Berlin, near, close, similar, terrible, awful, poor, carrot, apple, turnip, car, and bicycle. So basically, each of these words are points in this vector space. And I've colored the words in the different lists together. So we find near and similar appear very close together. London, Paris, Berlin kind of spread out a little bit. All of our vegetables are right close together there. Bicycle and car are in green there. So we can start to see that there are certain dimensions within this large vector space that allow us to easily visualize the distance between words and understand that as different meanings. So what are some uses of vector spaces? Well, we can do a dimensionality reduction. If we have a very large vocabulary and we have, say, tens or hundreds of thousands of dimensions, we can use this vector space language model to project onto a lower dimensional space, as I did in this figure. And that means that our feature vectors go from having tens or hundreds of thousands of dimensions to just 2 or 3. We can also do search queries. If we're given a word, we can very quickly find related words. And another interesting application is to look at word meanings and how they change over time. So certain words that have different associations will migrate through that space of meaning, and that's something that we can visualize and get a really deep understanding of the changing meanings of words.